We kind of go like, wow, that's great. We kind of project our own expectations on what this machine should be doing and how intelligent this machine should be, because it's able to just simply raise eyebrows and like, oh, I am surprised. Oh, that's amazing.
ITCS Pizzatime Podcast. Cheesy questions and juicy answers for the tech community.
Hi alle miteinander. Heute haben wir wieder ein wenig Live-Feeling vom ITCS Online 2020 aus Darmstadt für euch. In seiner englischsprachigen Keynote erklärt uns Professor Dr. Danko Nikolić anhand sehr einfach zu verstehender Konzepte, was die Unterschiede zwischen KI und menschlicher Intelligenz sind. Was sind die Kosten für KI-Systeme? Was gibt es für verschiedene Modelle? Und wo sind die Limits der KI? Also dann, viel Spaß!
To answer all these questions, I will discuss today 7 limitations, 7 factors that limit us in developing really smart, intelligent robots or artificial intelligence. So let's start with the problem number 1. We do not know how the brain works today. So I have spent myself about 2 decades in neuroscience and in cognitive science studying how the brain works, and I can tell you, we really do not know how the brain works. Yes, we know lots of things about brain, we know lots of details, but this really important thing, the key thing that makes the brain so smart, so intelligent, so cognitively capable and conscious and so on, we haven't figured that out yet. We are just not there. And that's really important because we don't get help for AI. If we don't understand how the brain works, it's really hard to get AI going. And the other way around, of course. So the second problem is the problem of scaling. So all the theories we have in the brain research and all the solutions that we have today in artificial intelligence, they both have the scaling problem. They don't scale well. And when I'm talking about scaling here, I mean scaling in intelligence, not scaling in a number of users served and so on, but scaling in intelligence. So compare this. We humans have our excellent civilization, scientific achievements, arts achievements, and so on. Apes do not have that. And yet, our brain is not that much bigger than their brain. It's only about 3 or 4 times bigger, our human brain, than a chimpanzee brain. It's not a big difference, right? Especially if you count in the factor that our bodies are bigger and the brains have to be bigger just because the bodies are bigger. So elephant, for example, has a much bigger brain than humans. It's not much smarter, but because of the body size. So our human brains are a little bit bigger than what our body requires. And that factor is maybe factor 2. Not even 4, but a factor 2. We just get our entire civilization with twice as big brain. Now, when we compare that to our technology for artificial intelligence, we don't see such scaling. So here's one example. You have these various solutions for this AI problem of recognizing handwritten digits. And on the right, you see a graph where you have intelligence of various solutions defined as performance, as percent correct. And on the y-axis, you see the amount of resources that are needed, like the size of the model. Here I plotted number of units in a deep learning model, but it could be something else, number of synaptic weights and so on. But what you see immediately is that a small increase in performance requires a huge increase in the number of resources. Very small models will do quite well, and then to improve this performance, you need to put 10 times more, 100 times more, 1,000 times more resources. This here is another one, plot that recently published by Microsoft, I think, because they proudly announced to the world that they have built the biggest model ever that has some 15 billion parameters, and this is for the purpose of NLP. And you see again this exponential function over time of the size of models that we are increasing. The intelligence of these models is not increasing particularly much. It's not getting any close to human intelligence. And yet, the amount of resources needed just explodes. And that's the reason why we had to wait so long from the invention of deep learning, which happened somewhere in 80s like long ago, 40 years ago, and to have something usable now. The very reason for that is that we simply did not have computational power for all this amazing, huge demand on resources. And it's not only computational power, it's the number of training samples and amount of memory and so on and so on. And that's our key problem for the technology of today. The intelligence growth is associated with an exploding growth in the amount of resources. Now, if you look at the mouse is not bad at all. Like the difference between us and mouse is not huge at all in the terms of the size of the brain. It's maybe 100 times bigger, the size of the brain. If you count in our body size and the need to increase the size of the brain just because of the body size, mice are somehow as intelligent as we are in that sense. Their brains are also a little bigger than what would be expected from their body size, and so are some of the dolphins. So mice, human, and dolphins have bigger brains than they really need for the body size. So that's what makes us extra smart. But all these numbers are small differences in the sizes of the brain. There's nothing like we see in the technology today. Problem number 3. We keep tricking ourselves when we develop some artificial intelligence. We sort of project our intuition into intelligent solution. Let me show this example here. That's a robot. That's not a real person. And the robot has some sort of a rubber face and motors that move the face around. And then if you talk to this robot and if it responds to you, it will make some face. Like maybe this is a disgust face, but it could make a surprise and so on. The thing is that this machine is not really intelligent. And yet we fall for it. When we see it, we kind of go like, wow, that's great. We kind of project our own expectations on what this machine should be doing and how intelligent this machine should be because it's able to just simply raise eyebrows and like, oh, I am surprised. Oh, that's amazing. And that's a kind of a thing we like, our brains fall for. And the reason is this. We like puppets as kids. We project into puppets personalities and so on, although we know that these are not really intelligent. And also to cartoons. We have been doing it all the time. And that's the problem we do also in artificial intelligence. We make this little trick, like a puppet, like a cartoon, and then we kind of get inspired to think, oh, we are making progress in AI. Not really necessarily, because what's behind has not been really improved. It's just the surface, like this face of this robot. And problem number 4. Now I'm coming to a problem that is sort of mathematical. It's a heavy mathematical stuff that has to do with the theory of machine learning. But I will simplify it as much as it's humanly possible. And to do that, I will use this example. Let's say you're preparing for a safari trip. You're going to go, 3 months away from a civilization with this car. So you will need some tools if the car breaks up. So what would happen if someone tells you, pick one of these tools to bring with you on the trip? You would say, no, I want all of these wrenches to bring, not just one. And I want even more wrenches to bring. Why would I take just one? So the reason why you don't take just one wrench is the same reason why we do not have just one machine learning algorithm. It's the same problem behind. When one machine learning algorithm is good for one type of problem, it necessarily becomes bad for another type of problems. And that's a fundamental mathematical property of machine learning algorithm that cannot be changed. There's no trick. There's no way around it. If you make the same thing with these wrenches, if this wrench is good for one type of screw, it's not going to fit the other type of the screw. Exactly the same problem. And it's called no free lunch. In machine learning, we have exactly the same thing. And that's why we need to have so many different models. Problem number 5. Now, we are coming to some problem that's founded in this no free lunch, but there is more going on here. Let's say you say, okay, no, I will trick this thing. I will take this wrench with me. This is called a French wrench. And in machine learning, you could call it, it has a general intelligence because it can fit any problem. It can fit any screws. You can come up with mathematical sort of structure that in principle can fit any possible intelligence problem, so you can come up with a tool that can fit any screw. So you say, that's my solution. But of course it comes with a price. And the price is that it doesn't fit really well none of the screws. If the screw is in some small space, you cannot approach it with this big guy. And if you have a really, really small screw in a watch, how are you gonna use this one? So it's, again, no free lunch. You again have to pay some price for this generality, which is then not really a generality. So when we move from a general set of model with some general set of equations, and when we narrow it down to very specific problem, that's what we call in machine learning inductive bias. We transform the model from broad to narrow, we give it some inductive biases. Now let me give you an example. Let's say we have these 3 mathematical data points. We want to fit them. And let's say I take a model in which I put in already sinusoidal equation. And I fit, there you go. It fits a sine wave quite well. And I can estimate the amplitude of the sine wave and the phase and things like that. That's inductive bias. I have put my knowledge in it. Is it a good idea? Sure. The same thing as with wrenches. It's a good idea if I got it right, if I just had the luck or had an extra knowledge that it was the right thing, right? So then I don't need these extra data points, right? But it could have been also like this. And then I would be completely off. It would be a wrong wrench. Like I have size 10, but the screw is size 15. Just useless, right? So what do we do? Which one do we choose? Well, what we do in practice in machine learning is that we use all of them. Like going on this trip, you want to have, a whole big, toolbox with all kinds of tools, and the specialized one and the general one, and as much as possible. And that's what we do in machine learning. And so we have models that are sort of more general, but clumsy. Deep learning is one of these examples. It's a more general model. On the general side, there are even more general ones than deep learning. And then we have a more specialized model, like decision tree is quite specialized, linear regression is quite specialized. And we combine them as you would be fixing the car. If your car breaks down, you open the tool, you look which one you have. You first look at the specialized ones. If you don't have a perfect fit with specialized one, then you go for the broad one. Right? Now, but you always pay the price. There's always some price to pay. And let's see the currencies with which we pay the price. There are basically 2 types of currencies, 2 directions in the space. We have here changing architecture of the model. Sometimes we call it model assumptions. You remember my sinusoidal functions. That's on the x-axis. On the y-axis, we have generality. So what is the currency with which we pay for these lunches in machine learning? One currency is the scope of applicability. Right? So if we narrow the model, it's not very much applicable. Like in this example, you have very small target where you can work and nothing else. And the other price we pay is computational power, resources, training data, electricity at the end, right? And that's what you have with deep learning model, right? You have seen the previous talks here. You need a lot of data to train deep learning models. That's exactly the price you're paying. And you cannot get away from that. Right? So let's see the vicious cycle. The vicious cycle is the following. You take some model, and it works for something but doesn't work for many other problems. So what you do, you provide some generality. You kind of broaden its capabilities. Usually it comes with a larger number of parameters to be fitted. What happens then? You cannot get enough data soon enough, or computational power. As we have seen, it's exponential growth in demands. Then you have, okay, it's not going to work. It's too hard. It's too heavy, too big. So what you do, you provide more specificity. And the more specificity you provide, then again, you're back to this problem that does not work anymore for many problems. It's very specific types of problem that it works. And that's a vicious cycle we have to work with. Intelligence has to work with, including our brain. And our brain has some unique solution to that, which we did not figure out yet. As we said, we don't know how our brain works. Problem number 6. We do not have a general theory of intelligence. So what I mean by general theory of intelligence? It's not a theory of general intelligence, not at all. It's a general theory of all intelligences. We don't have such a theory. Now, what I mean by such a theory, let's look at the general theory of information. And let us remember that back then, before we had a general theory of information, information was a very abstract concept. Nobody knew what it meant. You could mean this by information, that by information. You could have a long philosophical discussion. What is information? If an apple falls from the tree, is that information? You could discuss it to infinity. But then came the theory that made some conceptual definition, like you see here, source and destination and a channel and a noise, and then came up with some mathematics and some diagrams, and then suddenly everything was resolved. Today we have no more discussion, no more problems. We work with amounts, quantities of information very efficiently. We can calculate how much information can fit in our memory. We can calculate how much memory is needed to store a book or a movie, how much of a channel power we need to send signals to Mars or back from Mars to Earth. It's all doable. Everything works out with this general theory, mathematical theory of information. We have nothing similar for intelligence, and we need it. Problem number 7. There is a fundamental difference between how minds work, human minds work, and how human brains work. Let me explain you what I mean. On the example of a smartphone, let's say you are interested in working how the smartphone works, and you ask a grandma, the grandma principles, the grandma explanation of how smartphone works. And grandma will tell you, well, you swipe things with fingers, you tap here for recipes, you tap here to call my granddaughter. That's how smartphone works. For her, for an engineer, a smartphone works differently. It has lots of technical engineering concepts like ones and zeros, CPU, RAM, GPU, and so on. Two different worlds. The same thing applies to our mind and brain. What we observe as our mind thinking, acting, making decisions, it's the grandma principle. And that's what we can see. What's happening behind is the actual how the brain works, and we don't see that. For that, we need research. That's really hard to get, and we still did not get it. So the way how we build intelligence today is using grandma principle. Most of the time, AI researchers, machine learning researchers, what are they doing? They are thinking how to figure it out. They don't know how the brain works, so they're thinking how to figure it out. And what are they thinking? They're thinking about their own thinking. How would I do that? How would I think about it? How did I solve this problem? How did I distinguish this object from that object? That's not how the brain works. That's the grandma principles. In fact, the entire math, the entire field of mathematics is just thinking, just observing our own thinking, writing it down in terms of a symbolic process. It's all grandma principles. How we do it. Okay, the last thing that I want to point out, I have some great ideas on how to solve these problems, and I started writing a book. I call it Next Generation AI, and it will not be out soon. You will need some patience if you want to read it, but please be patient. And let's go now to conclusions. So we are still struggling to create AI. There's nothing infinite about intelligence. To the contrary, intelligence is not easy, and every step is hard. Here are some more conclusions. Intelligence is full of trade-offs, as we have seen. There's no one intelligent solution for everything. Specialization is necessity. We always have to specialize. And our own brains are also specialized. Human brains are specialized as well. And this then means that ants, they have to be better than us for some things. Their brains have to do better in some tasks than our brains. But also it means that our own brains are better than any aliens that could come in from advanced civilization, right? So next time when you run into an alien, and when the alien starts bragging about their civilization and technology and I don't know what, just tell them, sure, but can you do spaghetti? And they'll be embarrassed for sure. Okay, so thank you very much.
Thank you very much. It was very amazing. And I'm starting with a difficult question, but I think you have a good answer.
I hope so.
I say it in German, okay? It's easier for me.
That's right.
Lässt sich künstliche Intelligenz aufgrund seiner Verhaltensweisen diskriminieren, wie wir jetzt zum Beispiel wie andere, also wie Menschen diskriminiert werden? Ist das möglich?
Ja, ich glaube schon, es ist möglich. Ich weiß nicht, ob es schlimm ist. Es ist möglich auf jeden Fall, aber für die künstliche Intelligenz heute würde ich sagen, es ist nicht schlimm. Also die künstliche Intelligenz würde nicht traurig sein.
Ja, das auf jeden Fall.
Das würde ich sagen. Obwohl der Robot konnte so machen, ich bin traurig. Es ist nicht traurig.
Ja.
Es ist nur ein Trick.
Ja, das stimmt. Aber der Hintergrund ist einfach, kann man das machen, weil der Computer lernt ja quasi, was wir ihm beibringen.
Ja, das ist eine andere Frage, ob der Computer lernt zum Diskriminieren. Ja, das ist ein anderes Problem. Aber das ist dann Problem von unserer Seite, wie wir das organisiert haben, wie wir die Daten gesammelt haben, die Daten vorbereitet haben. So, es ist unsere Schuld, nicht von der Maschine.
Genau, da sind wir beim nächsten Punkt. Sie haben mal gesagt, ein Roboter müsste auch in den Kindergarten gehen, um Intelligenz zu lernen, wie wir Menschen auch. Was kann man sich genau darunter vorstellen? Können Sie das ein bisschen näher erklären?
Ja, kann ich. Also ein großes Datensatz zu bauen, in welchem man alle möglichen Kombinationen von Verhalten hat, um KI zu trainieren, ist nicht möglich, weil dieser Datensatz wäre viel zu größer als der Universum oder so. Irgendwie müssen wir einen Weg finden, unser Wissen durch Interaktion mit Robotern zu übertragen. Und dann, das machen wir sehr effizient mit Kindern. Also wir haben eine menschliche Zivilisation, die wir für 6.000 Jahre oder so gebaut haben. Und jede neue Generation von Menschen kriegt diese Zivilisation. Die müssen nicht von Anfang an arbeiten. Und was wir machen, wir programmieren die nicht, wir haben keine Training-Datensätze, wir einfach interagieren, wie in einem Kindergarten. Also man muss, um unser Wissen effektiv nach Roboter zu übertragen, wir müssen irgendwie wie in einem Kindergarten mit dem interagieren. Natürlich gleichzeitig muss man die KI-Technologie besser haben, wie das menschliche Gehirn, die funktioniert ähnlich wie menschliche Gehirn, sodass die so schnell mit kleinem Zahl von Interaktionen schnell lernen können.
Aber sehr spannender Vergleich, ja.
Ja, das ist die Idee.
Ja, schön. Dann vielen, vielen Dank für Ihre Zeit.
Gut. Ja, und ich bedanke mich auch.
Also, meine Nudelkochkünste sind auf jeden Fall jedem Alien überlegen. Wie fandet ihr die Keynote? Schreibt uns doch auf Social Media. Die Links sind in den Shownotes. Und wenn ihr mehr wollt, vergesst auf keinen Fall, ein Abo auf eurer Lieblingsplattform dazulassen. Und ihr könnt uns natürlich auch gerne auf Apple Podcasts bewerten. Wir bringen jeden Sonntag neue Episoden und freuen uns schon auf nächste Woche. Bis zum nächsten Mal. Ciao.
ITCS Pizzatime Podcast.